Hello class. So on this video, we're going to cover section 6.5. Right? In the previous video, we covered section 6.4, which was just this example, right, of using the Laplace transform to calculate or to solve an initial value problem in which our g of t or g of x is given by a piecewise definition. Then again, I mentioned that this happens a lot in applications. You could have so in an example of the spring mass system, which I mentioned here, and I talked about this in the previous video, you could have a driving force or a motion force just acting on your system just on some given intervals. And you can change that force function on different intervals, right? So you can take control of that by defining g of t as a piecewise function. So that's the idea, and that happens a lot. Now in section 6.5, right, so section 6.5 in the book, we're going to talk about another very common sort of g of t function that occurs in practice. Right? So let me give you two examples. Right? So suppose you want to model a system. Right? And two examples are going to be either a circuit board, right, or a spring mass system with specific and particular properties. Right? So for the circuit board, suppose that you have high voltages occurring for very short intervals of time, very short intervals of time. And in this case of the spring mass system, think of a force being applied to the system, so a driving force that drives the motion on a very small interval as well, or for a short period of time. These are situations that happen a lot. And these are just two examples of where these things could happen. But they happen a lot, and I thought that because of that, it's important for us to cover this section. So it's not a section that I covered last summer, but again, it's important, and since we have time, and it's not that complicated, really. The only complicated thing is going to be defining how we model or how we write these forces as a function, right? But other than that, it's pretty easy. Now, think of those two examples I gave you. How would that look like graphically? Right? So suppose we have a g of t in the case of for example, the circuit board, and then for a very small interval of time, we have this really high voltage that we put into the circuit. Okay? So graphically, this could look something like this. Right? Suppose that time happens at t equals, let's say, t naught. So what would this look like? Well, if it's continuous, and your function doesn't have to be continuous, it could look something like this. And then it gets really high, back down again. So this is an example of an impulse function. And again, you can see the graph, it looks like a function that has an upswing. So that's why it's called an impulse function. You can think of it that way. Okay. Again, you can see here that this is happening in theory for a small period of time, right? So this is a small interval. And so that's what an impulse function is. Right? Notice that this is very different than the examples we've seen before, because for the other examples, we're either working for large intervals of time, or the functions don't look like this. Right? They're either like some predefined function that isn't just like an upswing that immediately goes down, right? Or just an upswing, something just going up, even if it's not for a short period of time. So this is really something that we haven't covered in the class yet. Now, in the case that your function is not continuous, right, and your g of t doesn't have to be, it could look something like this. It's going to be a very similar picture. Oops, that's not straight. So a very similar picture. But if it's not continuous, it could look something like this. So at the same time, t naught, right, we're going to put in this high voltage into our circuit, or apply this really high, not necessarily, but for sake of explanation, a really high force on a small interval. Say that small interval is this. So what would our graph look like? It could look something like this. So it's 0, and when it reaches here, jumps up into whatever force we're plugging in as a constant, and then it goes back down. Right, so it could look something like that in the case that your g of t is not continuous. And again, it doesn't have to be. So that's how something like this would look like. And again, we haven't covered examples like this in class. Now, we're going to I'm going to give you a specific example of a function that satisfies this, and then we're going to define something more general that if you've taken some engineering classes, you might already have heard about this type of function. But we're going to talk about something called a Dirac delta function. Okay. So first, suppose d sub tau of t. As here, I introduce another Greek letter. So that this is tau. I think it's spelled like this. I'm not exactly sure, but it's a Greek letter. So suppose d sub tau of t is a forcing function in a mechanical system, right? So not necessarily a spring mass system, but just a more general mechanical system, satisfying an impulse behavior, meaning that the graph of this function, d sub tau of t, looks something like this. If it's continuous, it looks like the example on the top. If it's not continuous, it looks like the example on the bottom. So here I give you an example of one such function, right? So d sub tau of t being equal to the constant 1 over 2 times tau on the interval negative tau to tau, right? And 0 everywhere else, where tau is small. Okay. So again, let me graph this real quick. This looks very similar to the other picture. However, this is happening this is centered at 0. So the impulse is kind of happening. It's not that it's happening at t equals 0, but it's centered around t equals 0. Just like here in the previous examples, they were centered around t naught. Okay, so let's go here. So I'm going to have an interval here, negative tau to tau. And then our function is going to go up to 1 over 2 tau. And in this case, notice that it's not continuous. So our function would look like this. So here I'm including the endpoints on the bottom, right? So it jumps up here, and it does this. And again, what makes this different is the idea that tau is small. This is supposed to be a very short input, a very small time interval. Now, in the case where we're thinking of this as a force acting on a mechanical system, right, we can actually measure the power, not the power, we can actually measure the magnitude of this force. Right? How do you do that? Well, you can think of it graphically as if you want to measure the magnitude of the force, you would try to calculate this area here. Oops. Now, how do you calculate that area? Well, just calculate the integral from negative tau to tau of, this function. It's at 0 outside of that interval, right? So if we could do negative infinity to infinity, but it's just going to simplify to this integral here. And again, this is a measure of the magnitude of this force acting on this period of time, right? So we define this integral or this measure of this force as I of tau, right? Which again is this integral. It's just measuring the magnitude of the force. And you can verify, I'm not going to calculate the integral, but you can verify that it's equal to 1. Okay, so for t not equal to 0, we have two conditions that this function satisfies. And I'm not going to go over them in detail. I'm just going to tell you what they are. If we take the limit as tau approaches 0 from the right of this function, this limit actually goes to 0. And then the limit as tau approaches 0 from the right, so remember what's happening here is we're making tau smaller and smaller. So you can think of that as what these limits are doing. Should have said that before. So these limits are making the time interval shorter and shorter, as small as possible because it's a limit, right? So it's not approaching 0, but it's not equal to 0, but it's getting closer and closer and closer and closer to 0 infinitely. And this would better, right, and a sort of behavior like this would better measure what would happen, for example, in a circuit. If you insert a voltage, right, a high voltage, at a very short period of time, so think about how fast that voltage is going to travel. Right? It's basically going to happen you wouldn't think of it as even being a millisecond. I don't know how fast it is, but you wouldn't even be able to calculate that time unless you're having really precise instruments. Right, so that's why that behavior, as tau becomes closer and closer to 0, right, saying that tau is getting smaller, is important for us because that's what we're trying to emulate. So here I gave you these two properties here. Right, this function here, as tau becomes smaller and smaller, the limit is actually approaching 0. And for the integral, it's just always equal to 1. So think of these taus here in this picture that I drew for the magnitude of the force, or for this integral. These taus are getting closer and closer to 0, but the magnitude of this force is always equal to 1. Now, this is one function that satisfies these conditions. I gave you an example, right? D sub tau of t satisfies this. More generally, anytime we have a function that satisfies this, right, that sigma of t is equal to 0 whenever t is not equal to 0, and that's what's happening here, right? Because think of the graph again of this function as tau is becoming smaller and smaller. The interval in which your function is not equal to 0 is getting very small, right? So you can think of this a function satisfying these two conditions and then taking the limit as tau approaches 0 as saying that the function is 0 everywhere except at a single input. That's kind of what we're trying to emulate. Right? So in general, any function, and this is the Greek letter sigma. So I'm sorry that I'm introducing more Greek letters, but this is the common notation in basically every book I've read. Right. So a function, sigma of t, satisfying both of these conditions, that it's 0 everywhere except at a single input. So here I'm taking the input to be t equals 0, t not equal to 0, but this t could happen anywhere. And we can just do that by shifting the delta function, the sigma function. Oh, oops. Delta. Yeah, delta, sorry, the delta of t. Right. And then the second property is that the integral from negative infinity to infinity of delta t equals 1. And again, this function, d sub tau of t, when we take this limit as tau approaches 0 from the right, satisfies both of these properties. So this is an example of a delta function, specifically a Dirac delta function. Right? So how do you want to think of this? So the picture is going to be a little bit hard to draw. So again, it's centered at 0, but we can shift this anywhere we want. So if you want to see how this graph looks like, it would look something like this. And then here you have whatever value you have for your function, which would have to be 1 in this case because of condition 2. So let me do that in blue. Yeah, so in the case that it's not continuous, it looks something like this. Now, again, as I mentioned, we can shift this jump to happen anywhere by just shifting the delta function. Right? So if you said, if you want it to happen at, let's say, t equals 5, you would take delta of t minus 5, right? Shifting it to the right 5 units, etc. And again, you'll encounter Dirac delta functions in so many applications, right? Not even just in mechanical systems, and even just in theoretical applications that occur everywhere, right? A lot of times they occur in this non-continuous manner, right? So like the picture I drew here, but in other applications, they occur in this continuous manner, like as I drew in this example at the start, right? Where the jump is continuous, right? Again, they occur everywhere. Right? They're used a lot in all sort of applications. Now, can we compute the Laplace transform of the Dirac delta function? It turns out we can. Why? Because we're going to define it using this Dirac delta function we defined before. Right? So the Laplace transform of any Dirac delta function, right, so any function that satisfies these two conditions. Right? So where's the satisfies these two conditions? It's going to be given by the limit as tau approaches 0 from the right of the Laplace transform of this Dirac delta function that we had, right? Without the limit, it's not a Dirac delta function, but of this d sub tau function that we had. Okay. And just using the definition of the Laplace transform, and so just taking integrals, you see that this ends up being e to the negative s times t naught, where t naught is the shift. Why? Well, because you can think of this part here. So this part here, you can think of it as a step function. Right? So it's not too crazy that you get something like this showing up. What's crazy is that the limit as tau approaches 0 ends up being the same thing. Right? but this is what you get. Again, you can do it as an exercise if you want, just using the definition of the Laplace transform, or we're not going to do that. We're just going to give you what the definition is. Okay. So I'm not going into much detail in any of this. I'm just giving you the general ideas and not showing much of it, because again, the important thing for me, because this is not such an advanced class, is that I want you to know what these things are, how they show up, and then how to use them. So now let's do an example. Right? So solve the initial value problem, x double prime plus 2x prime plus 2x equals delta of t minus tau with initial conditions, right? X of 0 equals 1, x prime of 0 equals 0. So let's say this is a spring mass system. You could interpret this as some sort of spring mass system. There is damping, right? And then there is this spring coefficient, right? And we know that there is damping because of this term here, right? So we assume that it was proportional to the first power of the first power of the first order derivative, right? So think of this as a spring mass system with damping, in which at time t equals tau, at that time alone, we introduce this, or as a limiting process, right? We introduce this force or this driving force with a magnitude of 1. So that's how you want to interpret something like this. So let me write that down. This could be a spring mass system with damping and with a driving force of magnitude 1 at t equals pi. So that's how you want to think of something like this. Right? So anytime you want to model forces or currents or any other process that you have that happens in a short period of time, the Dirac delta function is useful. Now, let's solve this ODE. So we're just going to take the Laplace transform of both sides. I'm going to simplify the work a little bit. So the Laplace transform of the left is using the definitions from before. So it'll be s squared times the Laplace transform. Oh, it's x, right? So I'm going to use capital X of s. Capital X of s minus s times little x of 0 minus x prime of 0. So it's just the first term. Plus 2 times the Laplace transform of x prime is s times x of s minus x of 0. Right? So notice that I'm distinguishing between capital X and small x. Right? Plus 2 big X of s. Right? And this is going to be equal to what? Well, what's the Laplace transform of a Dirac delta function when the impulse happens at t equals pi? Right? By the previous definition, or just this formula, it's just e to the negative s times pi. Right? Again, maybe I moved too fast, but that's what the formula is. Right, so very simple. Now let's just simplify. So let's combine all of the x of s terms. So I have an s squared plus 2s plus 2 times big X of s. Now let's get control of the constants, right? So I have a minus s times x of 0, which is 1, right? So minus s, minus x prime of 0. Wait, is that correct? Yeah. X prime of 0 is 0, so we don't worry about that term. Then we have a minus 2 times x of 0. X of 0 is 1, so minus 2. And that's all I see in terms of constant. And this is equal to e to the negative pi times s. So now that you took the Laplace transform of both sides, solve for big X of s. Okay, so we're going to add s plus 2 to both sides. and then we're going to divide by this thing here.